Alright, so this video is about finding the limit algebraically, and we're going to find it algebraically because in this case, using L'Hopital's rule is probably not the most efficient way to find the limit. For example, as x approaches infinity in the numerator, you get infinity. It grows forever. As x approaches infinity in the denominator, it's also going to grow forever. So in this case, you think, well, I can use L'Hopital's rule. And if you try it gets kind of messy because now it will be the limit as x approaches infinity. This is a radical, so it's going to wind up being, the derivative of that would be 1/2 9x to the 6th, subtract x to the negative 1/2 times 54x to the 5th, subtract 1, all over 3x squared, and that's a 54 there. Anyway, so this is kind of messy. If you try to simplify that even further, you get the limit as x approaches infinity of 1 over 2 times 54x to the 5th, subtract 1, over the square root of 9x to the 6th, subtract x, times 3x squared. If we test that, that limit is also infinity over infinity, which means we can try L'Hopital's rule again. And it's going to go on and on and on and on and on, and it's not going to get any less complicated. So because of that, we should have other ways, other than just depending on the calculator. Because yes, you can plug it in the calculator and easily find the limit. So we can talk about using algebra to do it. And this is what I would do. With algebra, I can essentially divide the numerator and the denominator by the term of the highest degree. In this case, it's x to the 3rd power. So if I divided each part by it, I'll get the limit as x approaches infinity of the square root of 9x to the 6th, subtract x, over x cubed, divided by x cubed over x cubed, subtract 1 over x cubed. Alright, so the denominator simplifies pretty easily, giving you the limit as x approaches infinity of, the denominator becomes 1 subtract 1 over x to the 3rd. The numerator, though, because you got a radical there, you want to rewrite it so that that square root, that x to the 3rd can now go into the radical. So if you're going to make x to the 3rd go into the radical, it has to become something else. Because square root of 9x to the 6th, subtract x. In order for x to the 3rd to be divided into that radical, it's got to be the square root of x to the 6th. Why? Well, the square root of x to the 6th is x to the 3rd. So it's essentially the same thing. It's just a cosmetic adjustment. So with that being said, there's a problem in algebra. There's a theory in algebra that allows us to say that if we have a square root divided by the same square root, then we can divide the numbers underneath those radicals. So now that gives us a limit as x approaches infinity of the square root of 9x to the 6th divided by x to the 6th, subtract x divided by x to the 6th. And that's all over 1 subtract 1 over x to the 3rd. Alright, so from there, I can reduce this, like x to the 6 over x to the 6 cancels, leave you just 9, and x over x to the 6th gives you 1 over x to the 5th. So it's now the limit as x approaches infinity of the square root of 9 subtract 1 over x to the 5th divided by 1 subtract 1 over x to the 3rd. Now great, and when we find the limit here, we can now take the limit as x approaches infinity of the numerator and the denominator. So we got a limit of the numerator and the limit of the denominator. Now we should have had a discussion so far to talk about as x gets infinitely large in this fraction, this fraction gets smaller and smaller, closer and closer to 0. So as x goes to infinity, this approaches 0. Same case as this fraction. When x gets infinitely large, this fraction part goes to 0. So it basically leaves you with a limit as x approaches infinity of the square root of 9 divided by 1, which is the limit as x approaches infinity of 3. The limit of any constant is the constant, so the limit has to be 3. Now we could have found that with the calculator. This is the algebra of it all. So we can actually find the limit of that by dividing all the terms on the bottom and all the terms in the numerator by the highest degree, the term of the highest degree in either part, numerator or the denominator. And that's how we can solve that algebraically. Now there's an example in the textbook in section 4.4. I think example 4 explains this again. So if you need a second note or another way or maybe more explanation, you can start by studying that. That's all I have on that topic. Moving on. Alright, so this section of the video is about other types of indeterminate forms. Indeterminate forms discussed so far was 0 over 0, so L'Hopital rule can be applied. Another one was infinity over infinity, where L'Hopital rule can be applied there, and any infinity, like negative infinity over positive infinity, or negative infinity over negative infinity. All these are different indeterminate forms of the same type of infinity over infinity. And some others that were indeterminate was things like 0 times infinity. So in these, what we decided we do was we rewrite it so it's one fraction, so that then we can find it, use L'Hopital rule to finish it. And we had another one that was infinity times infinity. Again, we rewrite that as a quotient, so we can use L'Hopital rule to finish it. And the ones I haven't mentioned was infinity plus infinity, or infinity subtract infinity. And these are the two indeterminate forms we talked about in this section of the video. Basically, they all work the same way. In each of these other indeterminate forms, in this one, and addition of infinities or subtraction of infinities, each time we rewrite them in the form of infinity over infinity or 0 over 0 if we can. So no matter what's happening between those two terms, we rewrite them so that there's one quotient. So that's what we're going to do here. All right, so let's talk about it. All right, so take this example. It says find the limit as x approaches infinity of this function. So we thought about it. Limits can be expanded like this. The limit as x approaches infinity of the first term, x squared plus 1, subtract the limit as x approaches infinity of the second term, x. So if we just look at it right now, you might think, well, it looks like it might be infinity. It's probably going to rise forever or whatever. But if you check it out, this alone, this term alone, the very first term, is, as x gets higher and higher, the square root is going to grow forever. So this is infinity, subtract, and x gets larger here, it also raises forever. So it's infinity, subtract infinity. So this is an indeterminate form of the type infinity, subtract infinity. So if we're going to do this, the way we deal with it is, we deal with these by rewriting the terms as a single quotient. And that goes for had it been infinity plus infinity as well. Either way, we're going to rewrite the terms as a single quotient. So let's try that now. All right, so rewriting this as a single quotient, this is now going to be the limit x approaching infinity. I'm going to rewrite this first term as x plus 1, square root of x plus 1 subtract x in parentheses. I'm going to multiply it by the conjugate here. I'm going to multiply by the conjugate over itself, so it's really the same thing as 1. So we multiply by the conjugate, which is square root of x squared plus 1 subtract x, or x plus x now, over the square root of x squared plus 1 plus x. So that's the conjugate over itself of what's in parentheses there. So now, this is now written as one fraction, and that fraction will be the limit as x approaches infinity. I'm going to save some work. The product of this, well, this is over 1. The product of this times the numerator should be the square of the first times the square of the second subtracted. So it's basically going to be x squared plus 1 subtract this x times x is x squared. If you do the math, multiplying conjugates, it acts like the difference of two squares. So you essentially square the first and square the second one with subtraction. The denominator would be x squared x squared plus 1 plus x. And you might recognize that these negative x squareds and positive x squareds cancel. So it's now the limit as x approaches infinity of 1 over the square root x squared plus 1 plus x. And it looks a little bit simpler, but the only thing is now we've got a limit at the top. The limit at the top is 1. But the limit on the bottom is infinity plus infinity. So we still have a bit of the same problem we began with. So from there, now we have as a quotient, we have ways of getting rid of it. Like in the previous note, we talked about how we can rewrite this using the term with the highest degree and dividing everything by it. So right now, pause the video, copy down what you have. I'm going to need more space in this. So copy down everything you see, and I'm going to erase all this and continue it. So let's start from the last step. So what we learned in the previous note was we can simplify this without using L'Hopital's rule, because you might have chain rule happening and it might get really complicated. So instead of using L'Hopital's rule, even though you can give it a shot if you want, we can divide each term by the term with the highest exponent. So this exponent is x to the first. That exponent has the square root of x squared. So technically the highest exponent is this one, because the square root of that term, x squared, if you could square root it, would be x anyway. So I can divide each term by x. So this now means the limit as x approaches infinity of 1 over x divided by the square root of x squared plus 1 over x plus x over x. Which is really nice because that now gives you the limit as x approaches infinity of 1 over x divided by, in order to get that underneath the radical, it has to become x squared. So it's now going to wind up being the square root of x squared over x squared plus 1 over x squared. Plus 1. So that is now the limit as x approaches infinity of 1 over x divided by the square root of 1 plus 1 over x squared plus 1. All right, so, 1. So with that said, when x approaches infinity, I can see what happens to each of these terms. X goes to infinity, this becomes 0. This piece becomes 0. So I wind up having 0 over square root of 1, which is 1, plus 1. So 0 over 2. So 0 over 2 is definitely 0. So the limit there has to be 0. So anyway, so that's it. That's all I have on this topic. Good luck. Well, that's all I have. Good luck.